Today we discuss also measure theory part. In previous day we also discuss algebra, sigma algebra, and some example of sigma algebra, some example of algebra. We also today discuss about some proposition related to this sigma algebra. Okay, we'll talk about some proposition related to this sigma algebra. Let this collection A be an algebra. A be an algebra on a set X, and let A and B, and let this script A and B a sequence in script A, be a sequence in script A. Then there exists a sequence, okay, Bn in this script A such that what first Bm intersection Bn equal to phi for m not equal to n, and second union of n belongs to n, Bn equal to union of n belongs to n. Okay, so A be an algebra on a set X and let A and be a sequence in script A. Then there exists a sequence Bn in script A such that Bm intersection Bn equal to phi, and union of Bn equal to union of An. Okay, then what happened? That means then how we prove this one? Okay, we write here proof. We're also going to construction. Okay, how we construct P1 equal to A1 and P2 equal to A2 difference A1. Then it is easily B1 intersection B2 equal to phi, and B3 equal to, here we easily construct this one, A3 difference A1 union A2. Then obviously B3 intersection B2 is phi, and B3 intersection B1 is phi. Okay, now in this way we're going to that Bn plus 1 equal to An plus 1 difference A1 union A2 union dot 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 An. Then here Bi intersection Bj equal to phi for I not equal to j. Then in this way we construct this sequence. Then what happened? Then we also see that this one union of Bn equal to, where n belongs to n, equal to union of n belongs to n An. Okay, and obviously union of Bn equal to union of An, and Bm intersection Bn equal to phi where m not equal to n. Okay, now Now we erase this portion and going to further discussion about one proposition. Okay. Now we write this proposition. Okay. Here let x be a set. Let x be a set and a alpha belongs to this index set be a collection of be a collection of be a collection of sigma algebra on x. Be a collection of sigma algebra on x. Then what happened? Then intersection of alpha belongs to this be a sigma algebra. We have to prove this one. Okay. Then what we have to prove? So easily we do this. Let x be a set and a alpha belongs to this index set be a collection of sigma algebra on x. Then what happened? Then intersection of a alpha be a sigma algebra. Okay. Now we want to prove that portion. Okay. We write proof here. First we write that a equal to set a equal to intersection of a alpha belongs to this index set. Okay. then then what happened? Since x belongs to a alpha belongs to this index set, then what happened? If x belongs to a then alpha belongs to this index set. Okay. Since a alpha is an algebra, a alpha is an algebra, is an sigma algebra. Okay. So this x belongs to obviously intersection of, that means if this x belongs to a alpha, then obviously this x belongs to intersection of here a this one, not small x, this one is set x. Okay, belongs to this intersection of a alpha belongs to this because so simple that intersection of a alpha subset of a alpha. Okay, so this implies that x belongs to this a, this one equal to a. So we go getting first condition. Again we known about that phi belongs to this a alpha or alpha belongs to this. This implies phi belongs to this intersection of a alpha belongs to this. This implies phi belongs to this a. Okay. Now again we write here mark 2, then let A belongs to this script A. Then this implies A belongs to intersection of alpha belongs to this A alpha. This implies A belongs to A alpha for each alpha belongs to this. So this implies A complement belongs to A alpha, where A alpha is an algebra, is a sigma algebra. For alpha belongs to this. Okay. Then what happened? Then we is our portion and going to further discussion of that. Then we write here A. Then we write A complement belongs to alpha. This implies A complement belongs to intersection of A alpha. Alpha belongs to this. This implies here. Here we write A complement belongs to this capital A. Okay. So A belongs to this capital A. Okay. A belongs to this capital A implies A complement belongs to this capital A. Okay. Now we also erase that portion and going to further discussion of third property. Okay. Third property is that let an be a sequence in script A, and we have to show that union of n equal to 1 to infinity a n belongs to script A. Then a n belongs to this script A. This implies script of A n belongs to intersection of alpha belongs to pi this of A alpha. Okay. Then here n belongs to n natural number. Then what happened? Then a n belongs to any one of A alpha. Okay. Alpha belongs to this and n belongs to this. Then this one implies union of n equal to 1 to infinity a n belongs to this A alpha, since A alpha is a sigma algebra. So what happened? This implies n equal to 1 to infinity a n belongs to intersection of A alpha. Alpha belongs to this index set. Okay. Then what happened? Then we write hence intersection of alpha belongs to pi. A alpha is a sigma algebra. Okay. So here we write this one. Now we going to this smallest observation. This intersection of A alpha is the smallest sigma algebra. Okay, now we also construct one set here. Okay, right, let x be a set, let x be a set, and let script a be a collection of subsets of x. Okay, now suppose this a subset of this a on some sigma algebra. Okay, this one be an sigma algebra. And now obviously a subset of a2. Obviously this one be sigma algebra. Now this a subset of an sigma algebra. Then the smallest sigma algebra containing a is called the sigma algebra generated by the script a. Then the smallest sigma algebra containing a is called the sigma algebra generated by this a, and it is denoted by this sigma a. Okay, now sigma a is the smallest sigma algebra generated by a. Okay, now we're going to discussion about measurable space. Okay, we write measurable space. Here let script a be a sigma algebra. Okay, on a set x, then the order pair x script a is called measurable space. Okay, now we also going to the example of some measurable space. Here we talk about some measurable space. These are here xpx. Okay, xpx is one kind of measurable space. Be a measurable space. That means one example of measurable space. And we talk about now is that portion. Let a be Let A be a set in X, and then this script A equal to phi x a complement. Okay, phi a complement is a sigma algebra, and x this a be a measurable space, be a measurable space. Okay, be a measurable space. Now we're going to third option. We write here, let x tau be a topological spaces, be a topological spaces, and sigma tau equal to smallest sigma algebra generated by tau, smallest sigma algebra generated by tau. Then is called Borel sigma algebra, is called Borel sigma algebra, and bx or b small x or here sigma tau denoted by this one. Okay, then the space xbx is called Borel measurable space, is called Borel measurable space, measurable space. Okay, Borel measurable space. Okay, then now we also known about that another observations here, some closed sets, then union of these are in Borel set, and intersection of these open sets are Borel sets. We know about that. Okay, now some another collection, that means we know about that some Borel sets, we know about it. Now we also going to definition of another one, set function. Okay, set function, definition of set function. Which one is called set function? That means first we talk about algebra, sigma algebra, and discussion about that, then measurable space, then set function. Okay, let script A be a collection, let script A be a collection of subsets of a set X, of collection of subsets of a set X, of a set X, then a function mu a2 minus infinity is called set functions, is called set function. Okay, is called set functions. Now also denote this one in this way. Here we write x be a set a b c, and this script A equal to, here we write phi, here singleton A, singleton B, singleton C, okay, in this way. But we here write just, that means AB and then ABC, okay. Here we just write this one ABC, here C is C and this one is vanish, we not write now, here we write BC, okay. Then this one is, that means union of that, obviously here, and A complement is here, this complement is not here. Then we write here C again. So this one is an algebra, okay. This complement is here and obviously this one is an algebra and union of this is here. So what happened? Oh no, AC union is not here, we write AC here, and then again we have some problem. That means total power set is needed. Here we construct just A and AB, okay. A and AB, then here union is this, and complement equal to this complement, okay. This complement means this complement is BC and this complement is C in here and ABC is here. So what happened? Any problem is here? I think here not a problem, okay. Then no, there also one problem occur. That means A union C, AC is needed here and then B is needed here, okay. We construct PX and lesser we not, since here now this one is an algebra, okay. If we this one is an algebra, then our just assumption is going to example of set functions. So here set functions mu a, this collection to minus infinity to infinity, that means some number, that means mu of this A equal to what? 1. Mu of this BC equal to what? 2. Just one number belongs to minus infinity infinity. In this way we also define this one, but here this one is, that means one algebra. If we then talk about lesser then phi x is an algebra, and no, that means ABC and ABC, then this one is happen. Okay, if we just talk about ABC and ABC, then this one is not a problem, okay. Then this one obviously one algebra. Now we also talk about, in this way we define some set functions. That means we write here mu a to infinity, number of elements of this collection, then also this one is happen, okay. Some set functions are defined in this way, some collection to, that means minus infinity to infinity, This one is the range of this set function. Okay, then now we talk about some definitions, but today we stop here.